Chapter 4 Entropy Section 4.8 Entropy Change in Chemical Reactions. When we have a pure substance, we can calculate the entropy change given the temperature change and volume change. We can also compute the entropy change given the temperature change and pressure change. When the temperature change and volume change are given, we can either use this equation or this equation. They are equivalent to each other. However, usually it's easier to use this first equation to calculate the entropy change when ideal gas. We have Cv dt over T plus delta P over delta T on a constant volume condition Tv. If we have an ideal gas, delta P over delta T is simply Nr over V, and we just need to integrate Nr over V dV, and that's easy. What if we have a liquid or solid? In that case, delta P over delta T can be expressed as alpha over kappa. The reason we do this is because alpha and kappa are approximately a constant for a liquid or solid within a fairly wide temperature range and a fairly wide pressure range. That means we can just look up the numerical values of alpha and kappa for the liquid and solid, and we'll plug those values in. And the entropy change due to the volume change of a solid or liquid is simply alpha over kappa multiplied by the volume change. That's why for ideal gas we use this equation. For liquid or solid we use this equation. What about a real gas? We use the same equation for the ideal gases, but this provides us a approximate value for the entropy change of a real gas. Sometimes we're given temperature and pressure. Then we use this equation to compute the entropy change of an ideal gas. Again, these two equations can be proven the same. But over here, if we have the pressure change, it's just easier to integrate Cp dt over T, and then integrate this negative delta V over delta T dP. For an ideal gas, delta V over delta T under constant pressure condition is simply Nr over P. We just need to integrate this negative Nr over P dP for an ideal gas. For a real gas, we can still use this equation to get an approximate result. For liquid or solid, we use this equation. This is because alpha is defined to be delta V over delta T times V, or divided by V. Therefore, V times alpha is delta V over delta T on a constant pressure condition. And again, for liquid or solid, we can look up the value of alpha and then we plug this in here. And we have the volume of the liquid or solid, and then we can compute the entropy change due to the pressure change. We just integrate this, and volume, alpha are approximately constant, so the integral of this is just negative V alpha times the pressure change. Again, for an ideal gas at constant temperature, it's pretty easy to calculate the entropy change. It's just because when temperature is constant, this dt is 0, this dt is 0, and then ds is either delta P over delta T times dV or negative delta V over delta T times dP. Again, we can just use either of these two. If we use the first one, delta P over delta T is Nr over V, and then we need to integrate this. We get the natural logarithm of V final over V initial, and then multiply by Nr. That's easy. Over here we have a negative sign. Delta V over delta T is Nr over P. We can also integrate this. Alright, so this is the integral. We get negative Nr times the natural logarithm of P final over P initial. We can actually prove this equation and this equation are exactly the same because the pressure is inversely proportional to the volume. So P final over P initial is equal to V initial over V final. And pay attention to negative sign over here. The entropy of an ideal gas of pressure P can be determined given its standard entropy. So what is a standard entropy? That's just the entropy when this substance is in a standard state. For a gas, it's just 1 bar. So here, the difference between the entropy at pressure P and the standard entropy is simply negative NR times the natural logarithm of P over P naught. P naught is 1 bar. We get it from this expression. We can divide both sides by the number of moles. The molar entropy of an ideal gas with this pressure is the molar entropy of this same ideal gas under standard condition, which means 1 bar minus R times the natural logarithm of P over P naught. So for ideal gas, if temperature is constant, the molar entropy depends on the pressure. When we have a higher pressure, we have a lower molar entropy. For real gases, we'll just use the same equations to get approximate solutions. So what equations? Again, there's 2 equations. Now let's look at example problem 4.8.1. Calculate the difference between the entropy of 1 mole oxygen in air and 1 mole pure oxygen in the standard state. So the oxygen gas, well, of course it's a real gas, but approximately we can use these 2 equations. So the entropy of the oxygen at pressure P minus the standard entropy is negative NR ln P over P naught. And if we have oxygen in air, the partial pressure for oxygen is 0.2 bars. P naught is 1 bar. So we plug in all the numbers and do the calculation, we get 13 joule per Kelvin. This means the entropy of 1 mole oxygen in air has a larger entropy than pure oxygen in the standard state. How much larger? 13 joule per Kelvin larger for 1 mole oxygen in air versus 1 mole pure oxygen in the standard state. We know the oxygen gas in air is more disordered than pure oxygen, and this is just because we have 1 mole oxygen in air versus 1 mole oxygen in standard state. You have different volume. The 1 mole oxygen gas in air occupies a larger volume than 1 mole pure oxygen in the standard state, and therefore the energy of this oxygen in air is more dispersed, and that means we have higher entropy, because entropy is a measure of energy dispersal. So we have learned 3 different definitions of entropy. Entropy is a measure of disorder. Entropy is a measure of energy dispersal. Entropy is a measure of the natural logarithm of the number of microstates. For solids and liquids, we can use this equation when temperature and pressure change. So over here, this is the entropy change due to the temperature change. We just need to integrate this. Over here, this is the how entropy change depends on pressure change. And also, we can integrate this. The integral of the first term is just Cp times the natural logarithm of T final over T initial. The integral of negative V alpha dP is approximately negative V alpha times the change of pressure. This is just delta P. So if we have Ti, Tf, Pi, Pf, we look up the value of alpha, we get the volume of the substance. We just use this equation to compute the entropy change for a liquid or a solid. Again, we can do that only because for a liquid or solid, this alpha is approximately a constant. The volume of the liquid or solid is approximately a constant. Alright, that's why we can integrate this approximately. Now for a chemical reaction from A to B, at room temperature and 1 bar, we can compute its standard entropy of reaction. The standard entropy of reaction at room temperature is the standard entropy of product at room temperature minus the standard entropy of reactant A at room temperature. What if we do the reaction at a different temperature, such as 500 Kelvin? Well, we can just break down this chemical reaction at 500 Kelvin into 3 steps. The first step, A at 500 Kelvin, we change it to A at 298 Kelvin, and then we allow the reaction to proceed at room temperature to get B. And then finally we convert B at 298 Kelvin to B at 500 Kelvin. We make sure all 3 steps proceed under the standard condition. That means 1 bar condition. Now we can calculate the entropy change of step 1, step 2, and step 3. So this is the entropy change of step 1 from 500 Kelvin to 298 Kelvin. Step 2, the reaction proceeds at room temperature. Step 3, we change the temperature of B from room temperature to 500 Kelvin. Now we can just copy this here and then combine the first and third integrals. It's just the integral of 298 Kelvin to 500 Kelvin, and over here we have dsB minus ds sub A. Now if you look at this, we can rewrite ds as dq over t for reversible processes. So over here ds is dq over t, so we have this equation. And we do know dq is c dt, so dq of B per mole B is just CPM of B, alright, times dt. So we rewrite dq as c dt for B and also for A. When we look at this, it's just the change of the standard CPM in the reaction. So over here it's the change with a delta sign of the molar heat capacity under the standard condition. So again, this superscript means 1 bar or standard condition. More generally, the standard entropy change at temperature 2 is equal to the standard entropy change at temperature 1 plus integral. The integral from T1 to T2 of delta CPM dt over T. Delta CPM is the change of the molar entropy. This denotes the standard state. So this equation looks very similar to this equation for enthalpy at different temperatures. So the standard enthalpy of reaction at T2 is equal to the standard enthalpy of reaction at T1 plus integral. This integral is from T1 to T2, and we're integrating delta CPM dt. For entropy, we integrate delta CPM dt over T. So this is the only difference. So by deriving this equation for enthalpy at different temperatures, we can have similar derivation for the standard entropy of reaction at different temperatures. Again, these 2 equations look awfully similar to each other. Now let's look at one example problem, 4.8.2. The standard enthalpy of formation of ABC are these 3 numbers in kilojoule per mole at room temperature. We have standard entropy of ABC in this joule per mole Kelvin at room temperature. Now let's calculate the standard enthalpy and the standard entropy of this reaction from A plus 2B to C at room temperature. So how do we do this problem? Well, the standard enthalpy of reaction is, well, again, the product minus reactants. The product is C, we look up the value, and then minus A, this is A, and then minus 2B. This is minus 2B. We get negative 50 kilojoule per mole. That's the standard enthalpy of reaction. About the standard entropy of reaction, same. C is the product, so we use the value for C minus A. This is A minus 2B. We get negative 115 joule per mole K. That's the standard entropy of the reaction at room temperature. Alright, and now we're going to assume the molar isobaric heat capacity of ABC in problem 4.8.2. So this one, approximately this much, between this temperature range, between 25 degrees Celsius to 55 degrees Celsius. Now we can compute the standard enthalpy and the standard entropy of the same reaction at 55 degrees Celsius. First, we need to know delta CPM. So we have the product C minus A minus 2B. We get this number, negative 5 joule per mole K. So this is just a change of CP per mole reaction. Now delta H of the reaction at 55 degrees Celsius or 328 Kelvin is simply the room temperature enthalpy of reaction plus this integral from 25 degrees Celsius to 55 degrees Celsius of delta CPM dt. We have delta CPM, negative 5 joule per mole K. We integrate this, and then here we have the result, negative 50.15 kilojoule per mole. Note that the enthalpy of reaction at 55 degrees Celsius is negative 50.15. The enthalpy of reaction at room temperature is negative 50. These two are awfully close to each other. So later you will see very often in physical chemistry, if we know the enthalpy of reaction at room temperature, we usually can use the same number for the same reaction at different temperatures, as long as the temperature difference is not too big. In this case, the two temperatures differ by 30 degrees Celsius. However, the enthalpy of reaction, well, you can see they differ by only 0.3%. Now let's look at the entropy of reaction at 55 degrees Celsius. It's equal to the entropy of reaction at room temperature plus this integral of, over here, it's delta CPM dt divided by T. We need to integrate this. We do have delta CPM, which is negative 5 joule per mole Kelvin. We just need to integrate dt over T. The integral of dt over T is the natural logarithm of T. Therefore, we have this natural logarithm here, and we do the calculation, we get negative 115.48. Compare this number at 55 degrees Celsius and this number at 25 degrees Celsius. They're awfully close to each other. In pChem, again, we always assume that the enthalpy of reaction and the entropy of reaction at room temperature can be used at some other temperatures, as long as the other temperature is not too far away from the room temperature.